It's time to accelerate. Okay, so far in Unit 2, we've talked about distances and displacements, speeds and velocities. What we need to talk about now is what occurs when an object is speeding up or slowing down. We call this an acceleration. It's a change in a velocity, and this change in velocity is a vector. When we write acceleration, it is the variable a, and it has our little vector arrow on top of it, okay? It is a amount you're increasing your speed, or velocity rather. You're increasing or decreasing that velocity in a direction, okay? Which is velocity by definition. So you're changing speed in a direction. This acceleration can be a positive or negative number because of this. If we think about a little mathematics graph here, here's your number line, here's the positive direction, here's the negative direction. If your acceleration is pointing to the left, it is a negative acceleration. If it's pointing to the right, it's a positive acceleration. Now, as we're going to see a little bit later on, whenever we start talking about velocity graphs and position graphs and whatnot, just because your acceleration is negative doesn't mean you're slowing down. For instance, what if my velocity was pointing this direction and I was accelerating that direction? Anytime your velocity and your acceleration are pointing in the same direction, you're going to speed up. Think about it this way. You put your car in reverse and then you slam the gas. Are you speeding up? Yeah, you're speeding up. Just backwards, which is a little dangerous. It's only when your acceleration and your velocity are in different directions, such as if we had our car in drive going in a positive direction, and then we hit the brakes so that our acceleration was negative here, this would slow us down. Okay? So when our acceleration and velocities are in opposite directions, we will slow ourselves down. Same as if you were in reverse, and then as you're moving backwards, you hit the brake, your velocity would be to the left, but your acceleration would be to the right. Okay, so it's something to think about there. It's a little bit weird, but it is what we have here. Now, because our acceleration is given as a rate of change in the velocity, anytime we hear a rate of something, especially rates of change, we're thinking in an amount of time, which is a division here for time. And what we're looking at here is acceleration is just a change in velocity divided by time, which means that our acceleration is just a final velocity minus an initial velocity divided by however long that change was taking place. So sometimes, like here, we'll see it as the delta t, but sometimes you'll just see it as t if you're starting your count at 0, but it's just some change in time right there. This looks very similar to our velocity equation, remember, which was a final position. Oops, that's a position. A final position minus an initial position divided by a time. So look very similar. It's just now we're taking change in velocities divided by time. Okay. Because acceleration is a change in velocity divided by time, the units are a little weird for it. The units are actually meters per second over seconds. And if you looked at in Unit 1, we did a practice problem which was looking at a water balloon falling down. And that water balloon, the slope of that was 32 feet per second per second. That is this acceleration unit here. It's a distance divided by time divided by time. Often we'll just write this as meters, or whatever that distance unit is, per, and a second over a second is the same as saying seconds squared. Okay, so a meters per second squared or a feet per second squared is an acceleration. Looks a little weird, but it is what we're talking about here. Now, if we wanted to look at a little example, so down here, we have a car and it's changing its velocity as shown here. On the bottom numbers, these are times ticking up, and the top numbers are its speed. So at the beginning of time, it's not moving. It's at 0 meters per second. But a second later, it has a speed of 5, and then a second after that, a speed of 10, then a second after that, a speed of 15. So each second, this is increasing by 5. And if we take a look at this, we look at the acceleration equation, its final velocity is 15, the initial is 0, and the time interval here, 3 minus 0, is 3, which gives us a quick 5 meters per second squared, which makes sense because we're going 5, 10, 15. Through the middle here, in 1 second, it increases by 3 meters per second, but the second after that, it only increases by 2. So this is a 3 and this is a 2 for the accelerations. These are variable accelerations here. This is like you're not just stepping on the gas pedal, but you're stepping on the gas pedal and changing the amount you're depressing it as you're pushing it down. We cannot calculate a variable acceleration with this equation. This equation is for a constant acceleration. We can't use it here. It will only work for a constant acceleration, okay? That's because this acceleration we're calculating is technically an average acceleration over that time interval. So we don't really use it for these variable accelerations here. We use it whenever that acceleration is constant, or we're just looking for an average acceleration over that period. If we look at things at the end here, we're going 20, 15, 10, 5, 0 for each second. If you're taking a look at that, you can probably get the idea of what's going on. But if we look at our final and initial, our final speed is 0 minus our initial speed of 20 divided by our final time of 9 seconds minus the initial time of 5. This is just the time difference here. How many seconds was that? 1, 2, 3, 4. And we're going to get negative 20 meters per second over 4 seconds, which means that this acceleration here is negative 5 meters per second squared. And since this car is moving, we can say in the positive direction, since the car had a positive velocity here, that acceleration is a negative, and since they're opposing one another now, the car will slow down and come to a stop like we see. Okay, so this is just how we started thinking about acceleration. It's what we're looking at. It feels a little weird, but it is how we can speed up and slow objects down, which we do see a lot in just our day-to-day lives. So with that, this kind of content topic is finished. Let's take a look at some more examples and practice problems in the next few videos. Adios.